So I've been reading all of the comments left in the last two videos that I made about the Cybertruck. Fantastic comments, but those videos are worth watching if you missed them. I'll put a link in the description and at the end of this video. Anyway, it's become really apparent to me that there's a serious misconception about the stainless steel body. Like there's just so much misinformation out there. So I wanted to make this video to try to explain what's going on with that body and why it's shaped the way that it's shaped based on material considerations. So it's really an incredible piece of engineering that deserves to be understood. So let's do that, starting with the nomenclature, the 30x stainless steel that Elon keeps talking about. So here in this tweet that he did, he said you can't press form 30x stainless steel. Well, 30x, as most people understand it, means 30 times. They think it's 30 times hardened or 30 times stronger or something like that. No, 30x is just a reference to the grade of stainless that they're using, so the specific alloy. So here on this chart on the Continental Steel and Tube Company, we can see 301, 302, 303, blah, blah, blah. Now, not in this list is going to be like 307. I'm sure that's a grade. So one of these numbers is what Elon's using, or Tesla. It's not just Elon. There's a whole really clever team there. And that's what they're using to make the Cybertruck. But they're not telling us exactly which one. It must be some sort of a trade secret. Anyway, after they use this grade of stainless, then they're work hardening it. And that's where this extreme hardness, bulletproofness comes from. So we'll get into that more here in a minute. I wanted to kind of get to that, get that out of the way right here in the beginning of the video. So let's talk about first principles, right? Because Elon Musk always talks about first principles, and it's a really incredible way to do things. Now, it takes a whole lot of time to sort of start from square one, to just ignore everything that you know about a thing and question everything. This is what they, the ground up is what they were, Detroit used to talk about that when the all new blah, 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 designed from the ground up. But they didn't, right? That's why trucks still look the same as they have for 100 years. And the body on frame construction comes from carriages, horse-drawn carriages, when wood was very scarce. And so they would, minimize the use of metal by making the structure out of metal and then just building a bunch of wood on top of that. So that's where we're still stuck, because Detroit does not go back to first principles. They do not start from the ground up. But Tesla does. And probably, I'm guessing here, I'm not privy to the actual inner workings of Tesla, but probably they were looking at their factory. Somebody was looking at the Tesla factory. Maybe it was Elon, and he said, look at 25% of that factory is devoted to painting these vehicles. I don't want to paint the vehicles. Like, why do I have to paint the vehicles? Obviously, I have to paint them so that they don't rust. Well, hey, side note, Detroit loves the fact that their vehicles rust, right? That means that they sell more vehicles. Engineered obsolescence. Like, this is not tinfoil hat stuff. This is pretty much proven. Detroit controls Michigan to the point where, like, when Ford was on the up and coming, in the 20s and 30s, he was able to make entire towns where he owned the entire town. Every single house in that town was owned by Ford, and he rented it out to his workers. That's how much control Ford had over things there in Detroit. So you're going to tell me that somebody who could make an entire town all to himself is not going to exert some influence over the legislature to stop using salt on the road because it's rusting their vehicles more rapidly and making, the lifespan of their vehicles much lower? No. Ford and GM, all of Detroit wants their vehicles to rust so that you have to buy a new one next year. It makes them more money. And Detroit, time and again, has made decisions like this. Case in point, Carroll Shelby, the venerable Carroll Shelby. I'm a humongous fan of that guy. There's a movie about him out right now with Matt Damon, playing the role. And I was watching an interview with him. Maybe somebody can find it. I couldn't find it. I'll provide a link if you guys, leave a comment. But the interview was basically Carroll Shelby talking about the stupidity of the way that they were designing cars in Detroit. So at the time in Europe, they were designing small, lightweight little sports cars, but they were also putting small little engines in them in Europe. Exactly the opposite in the United States. They were designing these massive body-on-frame cars with all this steel. You got a steel chassis, then you got all this steel bodywork, and it was so heavy that they had to put these massive engines into them. And so that's what Carroll Shelby was describing. And he puts his head in his face palm and he goes, and they called them muscle cars. Right? Why? Why was Detroit selling cars like that? The answer was because they made more money the more steel that they sold. So they tried to put more steel into their cars so they could sell. It's this cahoots thing. It's this cabal that, the oil industry, the steel industry, and Detroit are all, that's one big monster, right? And they're going to screw the consumer over with engineered obsolescence at every opportunity. So along comes a guy named DeLorean, and he was an insider in Detroit. He was on the fast track to be like a CEO, or just he was a rock star there in Detroit. And he said, nah, I'm going to make my own company instead. So the number one thing that he went after was this rusting, engineered obsolescence thing. And instead of using paint, because painting is expensive, which means that the cars have to be more expensive. So instead of using paint, he went with stainless steel, and his frame that he was building his car on was all carbon fiber, like just a phenomenal thing to be made in the 80s. But, Detroit does paint their cars. Oh, we're painting the cars to resist rust, but they don't paint the undersides. Why don't their trucks come with standard undercoating, especially the ones they're going to sell in Michigan with all the salt on the roads? Those frames are bare metal, those truck frames. Why? Well, they want it to rust. They want you to buy a new vehicle. So yeah, DeLorean failed for lots of reasons, but the stainless steel idea is not new to Tesla. Tesla didn't completely come up with this, but they went back to first principles. They said, let's get rid of this whole corner of our factory and make our cars out of stainless steel. Now we can have 25% of our factory that we can devote to, battery production or something, which will drive the cost of these cars down even further. But hey, stainless steel, it's not enough. It's not just enough to be just rust proof. What else can we do with stainless steel? Let's think about how we can maximize this material. And so back to the grades of stainless and then the hardening. Let's see if we can get it harder, which also means stronger. Well, normally to harden metals, think of high carbon steel. What you're going to do with that metal is you're going to heat it up till it's red hot, like a magnet won't stick to it, and then you're going to quench it in oil. Just like you've seen in the YouTube videos, like the knife makers, they do this kind of stuff all the time. So probably you and I, the best illustration of this that we come upon daily is the blades for our our utility knives. So this kind of a blade. So if I took this, in fact, you know what? I'll just do it right now. I'm going to use these pliers and I'm going to bend this. I'm going to try to bend it, and watch. It's not going to bend. It's going to snap. See, it doesn't bend and deform out of shape. It snaps in half. So that is the perfect illustration of a stress strain curve. Let me show you what I'm talking about. So here in the vertical direction is the measure of stress, and here across the bottom is the measure of strain. Basically just a fancy word for the amount of deforming or the deformation that the metal undergoes. And stress is how much force you're putting on the metal. So a typical metal is going to start here at the 0 point and go straight up. So basically this is called the elastic zone, and as you put it under more and more stress, here increasing in this direction, basically it's going to strain, it's going to deform a little bit, but when you release the stress, it's going to go right back to its original shape. The metal is not, it's not deformed, so it has resisted the deformation. But somewhere up here, all metals are going to start to curve over. So they're going to start to do that. And when it starts to get into, this area, what's basically happening is the metal has permanently changed its shape. And once you release the stress, so you just, you drop the stress off, the metal is still going to look like it looked when it was under pressure, until it gets to a point up here where this curve is going to flatten out, and that is called the ultimate strength of the material. And then out here at the end, the stress strain curve just ends, just suddenly stops. And what happens right there is when, catastrophic failure. That's when the metal just completely fails and it can no longer, it's no longer a thing. It's broken in half. So in the case of the high carbon knife blade that we were just playing with, the angle of the stress strain curve was really steep, until it got to a point up here where instead of starting to gently sort of go, deform, to bend, it bent for a minute, but it was a very short moment of bending, and then it failed. So that's basically what the stress strain curve looks like for high carbon steel. Compare that to stainless steel, which is going to look something like this, where it's going to go up for just a minute, and then it's just going to start to slowly bend over. And the ultimate failure is, happening way out here where it finally breaks off. But, it's never going to reach the strength levels. In other words, it's never going to be able to resist as much stress as the high carbon steel did. That stress strain curve for this heat treated metal is pretty much a straight vertical line until it fails. Well, if you take this copper, right, it's got a sort of springiness to it. It's not spring steel, but the line of the copper sort of slopes over as you're going up, right? It's kind of bending. It will spring back into shape until it starts to bend, right? And so it'll start to bend and deform. You see, it's got a bend to it, but it's not catastrophically breaking. And this copper will still resist just about that same amount of push. So the stress strain curve on this one tends to go like that. And the copper is actually pretty close to the performance of stainless steel, right? Stainless steel also does this, which is not ideal for structure. You'd like it to be stronger, maybe not catastrophically fail, but you'd like it to be stiffer and stronger until it does fail. So you want to harden your stainless steel so it doesn't behave like copper. But you cannot heat treat stainless steel. It does not work to harden stainless steel, but you can work hardened stainless steel. We've all, anybody who's ever worked with this stuff has actually encountered work hardening. It's so frustrating as a material to try to drill holes in it because your drill bits just go dull. So everybody talks about how hard stainless steel is, but it's actually not when it's annealed. But once you work harden it, it's incredibly, like almost twice as tough, twice as strong. So how do you work harden? Well, let's look at this same piece of copper wire, and I'm gonna grab it with a pair of pliers here at the end. And then what I'm gonna do is I'm just gonna bend it right there at the pliers. Put a nice sharp bend in it. So you see I got a 90-degree bend. Now, I have not moved the pliers one bit, and I'm gonna grab that same wire and I'm gonna try really hard. I'm even gonna push right here on the edge, and I'm gonna try to bend it back to being perfectly straight. And what you can see is an S-curve. Why do I have an S-curve when I tried so hard to get it to go back to perfectly straight? And the answer is because this bend work hardened. As it was being bent, this material right there at the bend is now harder than the material next to it. So that stuff's going to resist deformation more than the stuff next to it, and it's going to come back up. And now that part's work hardened. So now if I tried to straighten it out again, it would, just continue to go on down the line. So work hardening stainless steel happens when you put just annealed, normal, hot rolled stainless steel into a press and form it. So the DeLorean, if you look at this design, had really strong wheel arches because there was a lot of movement, a lot of stretching and forming that happened on the wheel arches as that flat sheet of stainless was pressed into that shape. But look at all that flat area above the wheel arch. That metal did not get stressed or changed, shaped. So there's not a lot of work hardening happening in that metal. So that means that there's an uneven hardening to that entire quarter panel there above the front wheel. So the scratch resistance and the hardness and the structure is going to be great there at the wheel arch, and right there where it gets flat, it's going to be terrible, right? So Tesla doesn't want to deal with this sort of a deal. This sort of a problem. So the solution then is to use already work-hardened stainless steel sheets to make their cars with. So this is called cold rolling. So first they use a very hot metal to shape it into a rough sheet. Then when the material is basically room temperature, they shove it through some very intense machinery, just some gigantic rollers, and it squishes it down a little bit more. And so now that entire sheet of stainless, which is 3 millimeters thick, because that's the spec that Tesla's using. So 3 millimeter thick, work hardened uniformly across that entire sheet. Now the work hardened cold rolled stainless steel is going to look a lot more like the high carbon graph here, but maybe just not quite as extreme. Something like that. So it's going to be a whole lot stronger than what you're seeing here with the annealed stainless steel. But now it's so hard, like almost twice as hard. Here, look at this graph, right? It's almost twice as hard as annealed stainless, and you can no longer put that into a die, into a press and form it. Now, if you could, that would just be further work hardening it so it would stay the same strength. but it breaks the die. So obviously anything's possible in engineering. There's all kinds of you could use this massive press to force it into that shape, but that's going to cost money. And one of the constraints that Tesla has is they're trying to make an electric car for the masses, right? They're the modern vision of Henry Ford. And they're trying to make the best electric car you can imagine for the masses. Yeah. So die pressing forming it is out. And what construction technique do you have then? You have to fold it. So that's where the origami shape comes from. They're scoring the backside of the metal and then they're folding it along that scoring line. And that's why the truck looks so angular. So that is the constraint. That is where the aesthetics comes from. It is a function over form moment. But the trade-off for, not for violating everyone's expectations of this, sort of very curved looking vehicle is this incredible strength, right? Stainless steel is that cold formed, work hardened stainless steel is such a incredibly tough material, bulletproof, like Elon showed. It's going to be way more scratch resistant than what we're used to, like your kitchen sink or your refrigerator or whatever. That maybe you're used to using the wrong abrasive scouring pad to clean it, and all of a sudden you got a bunch of scratches on it. But that's just normal annealed stainless steel. It's not this cold formed stainless that's going to be a lot harder. So think about keys on cars. Keys are made out of brass. So brass. Here, look at this. Brass is a whole lot softer than stainless, so you won't be able to key a Tesla Cybertruck. So rocks, probably you'll get some really shallow surface scuffs from the rocks, but nothing too tragic. And you can buff them out. Speaking of buffing, how cool is this? You can polish stainless to a mirror shine, and it's not some sputtered plastic lie where it's plastic that looks like shiny metal. No, this is 3 millimeter thick. That's now shiny. You earned that shine, Mr. Shiny Tesla Truck. So I can't wait to see the first, sheik in Dubai who gets his hands on one of these things and shines the whole thing so that the sun is just blinding when you look at it. I mean, think about all those sports cars back, what was that, 10 or 15 years ago, where they were wrapping them with that metallic vinyl wrap and made them look like shiny metal. But that's a lie too. That's just vinyl. That's just plastic that looks like but it's not. This will be the real metal that's real shiny. So I think it's pretty cool. It's honest. The Cybertruck is a tool. Okay, so the aesthetics come from the fact that it's made to be the absolute best it can be, and it's not marketing BS. It's not hype like it is from Detroit. Built Ford tough. No, this is really tough. The only criticism that anybody has in all the comments about the effectiveness of the tool and the function is how difficult it will be to reach over the bedside. Okay, so there's one instance, maybe. I mean, I haven't been standing beside the truck. Maybe you're going to be able to reach through that sail pillar or whatever they're calling that. Maybe they'll put a hollow section there. So who knows what the final design is going to be. But okay, you got one small complaint about the usability of the truck, and everything else about the truck is built to be the ultimate tool. It boggles my brain how people can hate on this. It's nothing but revolutionary and awesome. But let's cover that a little bit more. Okay, so folding is the aesthetic. Well, there's obviously a whole lot of different shapes you could come up with as far as folding goes. Now, there's other considerations like how much do you fold it and how do you make those little tabs to spot weld it. And obviously the skin is going to be folded. It has to be folded because that's the cold rolled strong point. You want your skin, the outer fiber distance is the technical term for this in engineering. You want the skin to be where all the strength and structure is. That will make it the stiffest, strongest thing. But inside of the skin can be a whole lot weaker. So inside of the skin, you can still use the same alloy of stainless steel. So you can still spot weld it together, but it doesn't have to be that cold formed hardened. Right? It can be the softer, more malleable, annealed form of the metal. Clearly on this picture of the exoskeleton, you can see the inner workings are much more complicated as far as the shaping of them goes. So those have been die formed. And well, there is some work hardening that's going to happen from the die forming process. It's not nearly as intense as the cold rolling process is. So that annealed substructure, there's always two layers to a monocoque or exoskeleton or unibody, whatever you want to call it. There's always two layers to it, and one of them is going to be the structural layer, and that's the outside here. The inner also adds structure, but think about this. Back to the copper, right? The inner is that material that will behave like the copper. So even though it's bent a little bit, it's still going to spring back. It's still going to resist being further bent. So all the way through the crumple zone in the front crash, all the way through the crash, it's going to be resisting and pushing back and acting like a spring to absorb that impact energy. That's the inside of the exoskeleton at work there. So the Tesla Cybertruck is using a material that's far superior to normal steel. Or, I mean, this is an extreme example. This is obviously cars aren't built with high carbon steel, but normal steel still functions closer to this than it does to copper. So the stainless steel is more like the copper. So it's a superior material for absorbing impacts. Especially if they anneal the parts after they die press them. So they can die form them and then heat them up to get rid of all the work hardening that was gained in the die forming process. So it's going to be the safest vehicle that you've ever seen. Now I've covered the reasons for that before, where the fact that you don't have an internal combustion engine, that's basically a big solid chunk of metal that's really poor as far as crumple zones go. So the much smaller electric engine means you have a larger crumple zone. So it's just front impact survivability is going to be off the charts with this. It's going to be the safest truck that anybody's ever seen. And they figured out how to make the design aero. I mean, look at these simulations. I'll link them in the description down below here, but there's a great video here just talking about how the Cybertruck is more aero than any other pickup truck on the road. And it gets more and more aero the faster you go. So it's going to be great for battery life. But hey, I've got more videos coming on the Cybertruck. Here's a little motor with a pulse width modulation unit that I'm working on so that I can control the motor speed. And this is because I'm going to make a video further explaining differentials and why I think that the Tesla Cybertruck needs a torsion or worm gear type differential. So I'm modeling that so we can really talk about that in person. So stay tuned to further videos. There's more to come about this Cybertruck. Thanks for watching. See you next time.